Good morning, good day, good evening, everyone. It's 14 UT, and we are starting our webinar. And today's presenter is Dale Gary, who is Distinguished Professor of Physics at NJIT. He is Director of Expanded Owens Valley Solar Array. His expertise includes radio interferometry instrumentation and techniques, radio emission processes, and interpretation and use of microwave dynamic imaging spectroscopy for deriving parameters of the solar atmosphere, in particular solar flares. He has also investigated the impact of solar radio bursts as a source of radio noise and the effect of wireless communication navigation system. He has recently elected Vice Chair of the Solar Physics Division at AAS, and in the past he got his bachelor's degree from Michigan and then PhD from Colorado, I believe, and then he had history of working for Caltech and NJIT, where he works now. So, Dale, please go ahead with your 45-minute talk, followed by questions. Okay, go ahead.
And Gregory, you'll be monitoring if people want questions, right?
Yeah.
Okay, well, welcome. I'm glad to have this opportunity to tell you the new results we're getting with the Expanded Owens Valley Solar Array. It's a new instrument that gone online for a year ago. My title is thrown longer because we'll keep adding to it. So we added the microwave imaging spectroscopy as the feed in, but I'm going to tell you dynamic measurement of electron acceleration and coronal fields in a particular solar flare, but I have other examples if you're interested as well. I want to point out that this is not work solely by me, but has been contributed to greatly by Gregory Fleischman, Jelu Nika, Bin Chen, and Natsuha Kuroda. So let me see if I can make this thing go forward. This is the outline. I want to talk about the solar flare energy release and particle acceleration in a kind of general context. And then I'll tell you a little bit more about the Expanded Owens Valley Solar Array, and especially the observations that we made of this event in 2017, September 10. I'll then go through a little bit of a tutorial of the imaging spectroscopy method and how that is used to determine actual parameters in the flaring region. And then I'll talk about the implication of microwave spectroscopy for particle acceleration in the standard model, in particular looking at the erupting flux rope and the reconnecting current sheet, what we can learn about that sort of initial stage of the event, and then talk about the main phase and some observations of magnetic field decay, and then what are the implications of that for particle acceleration, and talk a little bit about the energy release evolution. So sort of in general, obviously the magnetic free energy of the solar corona is what's powering flares, and that has to come from the non-potential part of the field due to currents flowing in the highly conductive coronal volume. And somehow that stored energy can be released in a very short time, seconds or minutes. And that requires some anomalous resistivity or enhanced magnetic diffusion, which is going to cause the magnetic field to decay and release its energy. So in the standard solar flare model, here's a little cartoon of that. The location of the enhanced diffusion is placed at an X point behind a rising flux rope where the magnetic reconnection takes place. But clearly that volume is too limited and is going to require a very slow release of energy. One enhancement of that is to imagine a current sheet. So there are many small islands perhaps formed behind the rising flux rope. And in that current sheet, there are many sites of reconnection, and that sort of enhances the volume that's involved. But that's maybe still not enough. So I want to just kind of estimate the scale length of energy release. If you take a typical large flare, it releases 10 to the 31 to 10 to the 32 ergs of energy. And the energy density, of course, is delta B squared over 8 pi, where delta B is the non-potential portion of the magnetic field strength. And if you look at the energy release, then it's going to be that energy density times the volume, so delta B squared over 8 pi times some scale length cubed, and that has to equal 10 to the 32 ergs. If you adopt that delta B is, let's say, 100 Gauss, so you're actually releasing 100 Gauss of magnetic field, what volume does that require? So if you just do the calculation, you find that the scale length has to be 62 megameters, or around, that's almost 1/10 of a solar radius. So that's a huge volume of the corona that has to participate in this decay of 100 Gauss. Of course, if you have a higher field strength, that leads to a smaller scale length required. So you could say, let's put the magnetic field decay in lower in the atmosphere, down near the photosphere where there are high magnetic fields. But when you do measurements of the decay, or the, let's say, the evolution of magnetic field strength in flaring regions as measured in the photosphere, you find that the field before and after flares really yields a surprisingly small amount of change, and sometimes the field strength actually increases after the flare. So there's a cartoon, or just some examples here of one of these 12 different events from a paper by Duran, Kleint, and Calvo-Mozo, showing the magnetic field strength as the solid line, and the GOES light curve as the gray. And you can see that sometimes, like in panel A, indeed the magnetic field drops. But in others, like in B, it's actually increasing over the time. And so this is probably dominated by new flux rope emergence, and there's a lot of evolution in the photosphere, but it's not consistently a decay, and it's also relatively small amplitude. So we kind of can rule out that much of the magnetic field at low heights is contributing to this energy release. Now, we could also push it to low field regions higher in the corona, let's say 8 to 1 Gauss, but then if that scale length now mushrooms to 2 solar radii. So if you're going to do that in the high corona, you really have to encompass a huge amount of the solar atmosphere. So from these arguments, I would conclude that the energy release should occur over a large volume of the low corona, where the field strengths, the non-potential field strengths of order 100 Gauss are available to provide that energy. So that's where we would predict that it occurs. That's where the standard model actually has it occurring. I should say, just in passing, that the source of the strong fields in the corona, these non-potential fields, may indeed be a slower eruption of the field from lower heights. But once it gets into the upper, the sort of middle corona, that's where the energy release occurs. So if you think about other issues of the scale length, that another scale length bound comes from the total number of high energy electrons that are observed in X-ray and radio emission from solar flares. And the numbers are estimated to be of order 10 to the 35 per second. And if you work out how much volume of the corona is needed at typical non-thermal particle densities, you might say even 1 million particles per cubic centimeter still requires a scale length of order around 1/10 of a solar radius. And that has to be drained actually in 10 seconds. So you think that the flare would be over, but return currents can provide a way to replenish the lost particles so that you can continue to accelerate those particles. So we conclude that the magnetic energy release and particle acceleration must take place in a large volume of the lower corona and lead to a considerable reduction of magnetic field of order 100 Gauss on the time scale of about tens of seconds. So in the standard flare model, that current sheet alone seems to be insufficient to provide the needed energy and the needed volume. So with eOBSA, I'm claiming that with microwave imaging spectroscopy, we finally have the ability to measure the coronal magnetic field strength. And we can do it dynamically on the order of 1 second cadence. So what do we see? What do we actually measure in terms of that? So first I'm going to describe the instrument and the analysis procedures, and I'll show you a little bit about some details of the erupting flux row limb flare from 2017 September 10, and then I'll discuss the implications in terms of the results of the imaging spectroscopy. So the instrument consists of 13 of these relatively small antennas. A person would stand about as high as the mount here. So these are 2.1 meter antennas in diameter. What you're seeing here are actually 7 of these. And Gregory, are you seeing my pointer okay?
Yeah.
So there are 7 of these. There are actually 6 of them that are close by, and then there's a little dot way back in the back, which is the 7th one out of the 13. So that little one in the back indicates that this is actually a large area, about a square mile area over which these antennas are spread, and that provides the high spatial resolution, but only 13 antennas. So what can we do with 13 antennas? Now the key thing is that the frequency range is very broad. It's 1 to 18 gigahertz, so it provides a nice measurement of the spectrum, the radio spectrum over a broad range. We can make this one sample of the spectrum in 1 second, so it's very, very rapid. And so we can perform imaging spectroscopy at potentially more than 100 frequencies over that range. Now, I'm just going to show you a movie of the particular flare that I'm going to focus on. That's the September 10, 2017. So I'm going to play this several times. If you look at the panel on the right, you'll let me go ahead and play it. And I know that on WebEx this is sometimes pretty jerky, but you can see the AIA 131 angstrom emission. Let me go back and play it one more time. You see that flux row rising, and some very, very bright closed loops that are forming lower in the atmosphere. And the flashing is simply because there are 2 different two different exposure times, and so every other image is actually overexposed in those bright loops. Now, if you look at the left side, that's what I call a true color image of the radio emission. So what you're seeing there, we've taken each frequency and apportioned it into the red, green, and blue color planes according to its frequency. So the lowest frequency would go entirely in the red color plane. The highest frequency would go into the blue color plane. Some intermediate frequency, part of the brightness would go into the red, some into the green, some into the blue, and scaled according to its frequency. So what you're going to see when I play it again is some started out quite red because it's mainly low frequency, and then there's a period when it actually gets very blue. That implies that it's dominated by this high frequency. So let me go ahead and play it. You can see here it's become very blue, and you can see a general rising and also development into loops there. So this is kind of a snapshot. I'm going to play it one more time, showing the frequency content as well as the brightness and the spatial relationships of that. So that's great, but we'd like to do something more quantitative. So let me do a little bit of a tutorial of radio emission mechanisms, just so that you can understand a little bit better what we're looking at. The main ones for the microwave range are free emission, Bremsstrahlung emission, and that's just due to distant collisions of electrons with ions. So you have an electron that's trying to go straight through the plasma, and as it gets near individual ions, it feels a attractive force, and so the path bends around like this, but it's quite gentle bends. And those gentle bends are then releasing photons that are in the radio spectral range. What's important here is that the bremsstrahlung is dependent on density squared, so it's the same as X-ray bremsstrahlung, same kind of dependence. Gyro emission, on the other hand, is purely due to electrons spiraling in the magnetic field. So this is the V cross B Lorentz force, and there are no collisions needed. You don't need a plasma in order to produce radio emission from an electron in a magnetic field. So what's important is that this kind of emission can happen in low density regions of the corona. And of course, its importance is that it's purely proportional to the magnetic field strength. So at the lowest energy of the electrons, you just get the cyclotron frequency, which is EB over MC, a bunch of fundamental constants times the magnetic field. If you go to a little bit higher energies, you start to get other harmonics. It's because the emission profile of the electrons start to get asymmetric, so they're beamed forward. This is a relativistic effect, and so that beaming is causing the emission to be peaked every cycle, and that brings in additional harmonics. In the case of the sort of hot corona, but not particularly non-thermal, you'll have a few lower harmonics. But in the case of solar flares, you get mildly relativistic electrons, typically from 300 keV to 1 MeV. That range of energies results in a continuum spectrum generated by harmonics between, say, 10 and 100. And then finally, I should mention coherent emission. It's narrowband emission produced by the collective action of electrons due to the interaction with waves. For example, Langmuir waves that produce plasma emission we know as type 1, 2, and 3 bursts, or Whistler waves. So the kind of emission we're going to be focused on is this one, the gyro emission. So that's really the dominant emission that we're going to be talking about. So what about the gyrosynchrotron spectrum? I said it's a continuum spectrum. It looks more or less like this. It's got a, this is now in brightness temperature, so it's basically talking about the kind of temperature or energy content of the emission. And at low frequencies, you have a rising spectrum, generally fairly low slope, around 0.9. And then as it reaches a peak, then it falls because it becomes optically thin. So this is dominated by the equivalent temperature or effective temperature of the electrons, and then this is dominated by the emissivity. And this part of it is proportional to the power law index of the electrons. Now, the peak frequency depends mainly on the magnetic field strength. So if you double the magnetic field, it's going to shift that whole spectrum to the right to higher frequencies like that. And that was for a factor of 2 increase in magnetic field. Now, if you increase the density of the high energy electrons, it's going to also shift the peak a little bit, but it's going to go in a slightly different direction and much smaller amount for a given factor of 2 and increase in density or length. Now, finally, if you, or not finally, but if you look at the optically thin slope of the microwave spectrum, that constrains the power law index of the non-thermal electrons. So if you make the electron index flatter or the spectrum harder, then you end up with a flatter microwave spectrum. The low frequency optically thick spectral range constrains the effective energy of the radiating electrons. So if they are a higher energy population, then you're going to end up raising the brightness temperature. It's going to go up and down like that. And then the shape of the low frequency spectral region depends on the thermal plasma density, either by the Racine effect or by free absorption. So you're going to end up with this slope changing depending on that. So all of these parts of the spectrum are being used to constrain various parameters of the particles doing the emitting or the plasma. The shape of the high frequency spectral region I'm talking about up here also can constrain the high energy cutoff, or how high of the energy those non-thermal electrons get to. Now the problem is that if we try to measure the radio spectrum without spatial resolution, then inhomogeneity can spoil this nice diagnostic potential. So the microwave spectrum becomes some unknown admixture of spectra from different parts of a potentially complex source. So that's certainly true of the 2017 September 10 event, as I'm going to show you. So in this case, a microwave spectrum largely loses its diagnostic potential, and the spectrum becomes some broad thing like this. And you can see that in this particular example from Huangbo et al. In 2014, they were trying to fit a radio spectrum indicated by the blue dots here and then these red points here. And so they've done that with, what are these, like 7 different components. Each of these components would be a homogeneous source, but because of the inhomogeneity, you have to add them all up and you get a overall much more broad and flat spectrum. So in that case, you lose the diagnostic potential of the shape. But EOPSA, for the first time, provides spatially resolved spectra, so the multiple components can be separated in space. So this is now segueing to the 2017 September 10 event. What I'm showing in the upper plot is the dynamic spectrum. This is the total power spectrum with no spatial resolution from EOPSA. And this is about an hour of time. And the frequency range is going from around 3 gigahertz to 18 gigahertz. And you can see these are some plots of individual spectra, just time light curves. And you can see that the lower frequencies, there's a peak here early on, and then it rises to another main peak here. This is the red curve. And then at higher frequencies, the blue curve shows that that main peak is occurring a little bit earlier. So there's actually a dispersion or a delay from high frequencies to low frequencies in this main peak. But in the initial peak, there's almost no delay. Everything is sort of simultaneous. RESI energies show a similar delay. They show that the lower, all of these are non-thermal, 50 to 100 keV or 100 to 300 keV peak more or less at this earlier time, but the highest energies have a delay. So there's kind of an indication of continued acceleration and flattening of the spectrum. So if I look at the spectrum on a longer time scale, this is now more than 2 hours long, it brings in some additional fluctuations in the event quite late in the event. So those are what we call pulsations, and I'll be talking a little bit about that also in a moment. The point is, though, that we can make images for every frequency time bin in that dynamic spectrum. So that's a lot of images. Here's an example of just one snapshot in time. On the left are 28 different images, all at the same time, but at different frequencies. So you can see that at the lowest frequencies, the source is broad, and then as you go to higher frequencies, it becomes somewhat loop-like, and of course the shape and the positions of the emission are changing. It's awfully difficult to extract much information from this set of images, but if you stack them vertically into a data cube, so you have 2 spatial dimensions and a vertical frequency dimension, then you can drill down at different points spatially. So this is showing this 10.9 gigahertz map and showing 4 different points there. And if you look at the spectrum along that 3rd dimension in each of those, you see these spectra here. Now let's go to another time. It's just another, it's like a minute later, and everything has changed. All of the maps have changed. things, the brightness has changed in different places. But the spectra have also changed, and you can see that the spectrum at this time shows, at this source location, it shows a peak that's kind of rising. It doesn't really turn down. At this point, you get a bit of a turn down at the highest frequencies, but at higher up in the corona, you're getting more of a lower frequency peak, and then at the highest point, you get even lower. Okay, so then here's another time, another minute later, at those same 4 points, and you can see the spectrum is changing. So this evolution of the spectrum, we can actually, the points are, the black points with the error bars are the actual measurements, but we can fit, basically make theoretical fits to assuming a homogeneous source. So we're going to ignore the third dimension, and we're just going to fit a homogeneous source model to this. That model can consist of multiple parameters. Two of the parameters are the magnetic field and the power law index of the electrons. So for this particular time, you can see, let's concentrate on these three that are in the same sort of position angle, but at different heights in the corona. You can see the magnetic field is 290 at this lower height, 248 up here, and 155 Gauss here. So there's a drop in magnetic field as you go upward. And likewise, the power law index is flatter down here and becomes steeper as you go up from 2.5 to 3.4 to 4.5. So we can actually do this same exercise everywhere in the map. We don't have to just choose 4 points. We can do it in every point where there's emission. And we can do it at every time on a typically 1 second time scale. So let me show you a little bit more about the fitting algorithm. Again, the fitting is done assuming a homogeneous source, so we're ignoring any line of sight variation. But the imaging is allowing us to eliminate the at least the plane of the sky variation of the source spectrum. So many parameters can potentially be fit. In this case, we're going to fit 6 parameters: the magnetic, the magnitude of the magnetic field, the angle theta between the magnetic field vector and the line of sight, the thermal density, the non-thermal electron density, and this is the electron density measured above 20 keV, which is a fixed low energy cutoff for this exercise, and the power law index delta, and the high energy cutoff Emax. So those are the 6 parameters that we're allowing to vary in these fits. And the latter 3 parameters are used to determine the overall energy of the non-thermal particles. So the minimization of the fit employs the simplex method with shaking to guard against settling into a local minimum. So I'm going to play a little movie that's showing you the sequence of fitting attempts by this algorithm. And you can see that it relatively rapidly settles onto a good fit, but then the algorithm shakes the solution right there. You can see that it's now moved to a non-optimum fit, and now it's trying to do this downhill method to find the best fit. And it keeps doing that several times. The different shaking allows you to make sure that you sample a larger range of parameters and try to avoid going onto a local minimum. So every position in time in our images and our movies are bit completely independently. So if you see spatially or temporally smooth fits, that's an indication of the stability of this process. So this is the result. This is on the left is the magnetic field strength. It's the color bar is ranging from 0 to 1500 Gauss, and so you can just see on the scale up here. So in various places within the emitting region, you can see some very high field strengths. Possibly these are bad fits resulting from the fact that you really don't have a peak at those low frequencies. The spectrum continues to rise beyond the highest frequency that we go to. But in many places, certainly there are reasonable fits of order many hundreds of Gauss, and there are regions of lower field strength as well. Now on this side, you're looking at the electron power law index, which is going from 0 to 7 color bars. And so you can see that the higher heights tend to have larger values of delta, which means a softer spectrum, and lower heights tend to have lower values of delta and a harder spectrum. But let's go ahead and watch a movie. So we can watch this. These are every 4 seconds we're showing a different frame. And so this is just showing the evolution of the magnetic field and the power law index, all during about 4 minutes of the flare. And so that's a fantastic new capability that allows us to really do some quantitative investigation of this energy release. So I'm going to go into that in a bit, but let me go ahead and talk a little bit more about the event. So this is kind of an overview of the event comparing RESI and ELSA data. These are 3 different times in the flare, and in the right panels are a zoomed out larger field of view, and in the left panels are zoomed in this square box region. So in the zoom in, you can see the RESI contours a little better. The RESI contours are thermal, are the red contours. Those are 12 to 18 keV, so super hot thermal, and those are isolated to the bright UV loops. This background image is AIA 193 angstrom with an inverted color scale so that dark means bright and UV. So the red contours are showing you where the super hot thermal emission is, and then this blue contour here is 30 to 100 keV RESI source location up above those closed loops. So we know that there are some non-thermal particles up here. The radio emission is also in that region, nicely co-spatial with that, but extending higher. And the reason it extends higher is because the radio emission doesn't require high densities. The X-rays really require a region of high density in order to have that density squared emissivity. But the radio emission is not requiring high density, it's only requiring magnetic field strength. So you can see that the magnetic field is going down. That's why the the lower frequency sources are going higher. At the main phase of the flare, we have a similar effect. Maybe I should say in the zoomed out portion here that in addition to this main source above the closed loops and actually extending up to the current sheet, we also have these 2 outlier sources, which I'm going to talk about in a minute. So then at the main phase, the super hot and the non-thermal emissions are very close together in RESI, all inside of this already closed and bright UV loops. The radio emission continues to extend quite high up into the corona. And then about, this is at 1640, about 45 minutes after the start of the flare, the radio emission actually bifurcates into 2 sources on either side of the dense, what we call a plasma sheet that's left over from that rising flux rope. So this is 45 minutes later, and the emission is now bifurcated. So the RESI emission again is showing high energy particles and super hot plasma inside of the high density regions, but the radio emission is showing that those high energy particles are extending over a much greater volume than you would have gotten from just RESI. If we look now at the initial flux rope eruption, compare that with the standard model. Here's our standard model. It's best if we, hang on 1 second here. It's best if we turn this to the side so we get the correct orientation, and then we can identify the flux rope, and there's kind of a necking down of the radio emission here, and we've got a nice, the that sort of can be identified with the X-type neutral point perhaps, or the current sheet at least. And then lower down we have these closed loops and the region just above the loops. So in this kind of area here. Okay, so all of those parts are there, but we also have these outlier sources. So it's possible that those are the ends of the flux rope. So maybe this flux rope is rooted in the photosphere. Maybe we're seeing emission at the ends of the flux rope. But alternatively, we could be seeing an overlying field line, perhaps with an orientation that's opposite the magnetic field in the flux rope, and therefore you would get the legs of such a loop powered by breakout reconnection. So there'd be some reconnection here that is actually powering particles down to the legs. So it's an interesting supposition. I know that we have some folks at Goddard looking into that and exploring that issue. Now, along the current sheet, again, we can measure the magnetic field as a function of position. And this is a poster by Bin Chen, and he's working on a paper now. But it really nicely shows, this is a model, 2D model, showing this is the y component of velocity. So this is an upward going jet and a downward going jet. And in this region, the magnetic field is predicted to have a dip. So in this region of high velocity, have to conserve flux, so the high velocity implies a lower magnetic field strength there. And if we compare our measurements, which are these circles, we actually get a similar drop of magnetic field just in this region, which Bin is calling the interaction region. So it's intriguing possibility. These sources up here were imaged by subtracting the bright sources here, and then it kind of reveals better these weaker sources up here. And again, the lower magnetic field as you go higher in height, the magnetic field scale down here, is indicated by the rising location of the lower and lower frequencies in the radio emission. Okay, and I just want to make this point that there's continuous acceleration during this time. Even 40 minutes later, you're getting this emission that has to be continually powered by some kind of ongoing energy release. And even this is 100 MeV gamma rays. Those actually decay over about 12 hours. So it's a very, very long decay of these very high energy particles coming from somewhere. So it's an interesting long-term energy release and decay issue. And finally, for this event, I just want to talk a little bit about the pulsations that occur at the end of the event. So this is now an hour and a half later. These are Resi and Fermi different energies, light curves, and you can see that there's some fluctuations there that seem to be quite well correlated with the fluctuations we see in the EOFSA microwaves. And so what we're going to do is look at a movie of the positions of those. So on the left here is just AIA 335. On the right is the AIA with the Resi contours in dashed contours here, two different colors for two different energies, but they're actually co-spatial for this whole time. And then the kind of colored filled contours are the EOFSA images. So I'm going to play the movie, and you'll see this yellow bar here that is moving along to show you the time and what the dynamic spectrum looks like at that time. So here we go. And every time we come into one of these pulsations, you see that this part of the source actually kind of gets brighter. So the non-thermal particles seem to be down here. All of the emission up here is consistent with thermal superhot emission. So the Resi data end, but we continue to have the EOFSA observations up to this point. So you can see that the EOPSA and RESI are co-spatial with this region of right at the tops of these loops, but these are all consistent with thermal emission. In fact, if you take the DEM weighted temperature from an analysis of AIA, you get this image, and at that time, if you look at the location here, you would predict a radio spectrum just from this DEM information that looks like this line. And the measured one is the blue one. And then if you look at this region, this is again the predicted emission from the AIA, but the actual emission is higher. So this region appears to be containing non-thermal emission. So this gives you some idea.
5 minutes, then.
Okay. Gives you some idea of what you can do with EOS data. Now let's take a look at the quantitative look at the B field and how those change. So these are just 4 frames, 72 seconds apart from our movie. And what we've done is overplotted some contours that correspond to the AIA loop locations. So what we find if we look at 2 places in these maps, like the white pixel here, the time profile of the magnetic field measured from those spectral fits is actually decreasing to about 1558 and then becomes remarkably constant. And if you look at some higher point, you find that the magnetic field is again decreasing, but it decreases for longer and becomes constant at a later time. So the implication, one possible implication, is that the white contours here are showing the EUV loop emission at the time of the map, but we expected that those are cooler loops, right? Those are emitting EUV. The actual top of the newly closed loops could be higher, and in fact could be indicated by some later time. So these black contours are the EUV loop emission 10 minutes later, so that kind of accounts for the cooling time, and it would predict that this black contour of newly closed loops is passing that point around this time. And so this could be the above the closed loops region and then becoming closed and therefore becoming quite constant. The magnetic field decay rate is 5 Gauss per second. So let's take a look quantitatively at that. The Faraday equation would tell you, if you just do a scaling argument, that the electric field associated with that decay is of order 20 volts per centimeter. This is for a chosen non-uniformity scale length of around 5 arc seconds, which is the typical size of structures seen in the EUV. So we're just kind of guessing a scale length, but that scale length provides an estimate of this electric field. This is similar to electric fields measured in other flares. And those other measurements are based on ribbon motions. And that electric field is highly super Dreiser, which would imply the ability to accelerate both electrons and ions to high energies. The B field decay also implies that there's a magnetic diffusivity suggested by the induction equation given here. This has 2 terms. One of them is related to induction, so you have a possibility of decay in a certain volume due to just motions of the magnetic field leaving that region. But much of the decay we look at is widespread and decays in place. It's not just simply a motion of magnetic field out of the region. So that brings in the second term, which is the diffusion term, which includes this diffusivity parameter nu. And just again doing the scaling argument, you find that the parameter nu is something like 10 to the 15 square meters per second. So that's a high diffusivity that could only really be provided by turbulent motions. If you then look at the induction equation over a random velocity field, you get a renormalization of that gives you this expression where U is the typical turbulent velocity. So if you then use the turbulent velocities measured by Warren et al. In another paper, which is about 100 kilometers per second in that region of the cusp region of the flare. And that implies, using the same scaling R, implies a very similar number for the diffusivity. So there's an agreement between the measured turbulent velocities and this expected diffusivity of the magnetic field. There's also an energy associated with that magnetic field decay. So if you integrate over this box and look at what is the magnetic field, what is the magnetic energy doing as a function of time, you find that it drops quite rapidly over the first minute or so and then becomes relatively constant. At the same time, we can measure the particle energies in that box, and they're doing this. So the non-thermal energies above 20 keV are around 1% of the energy in the magnetic field. But this drop here implies a release of energy of 8 times 10 to the 30 hertz. So I'm just going to conclude here by saying that with the completion of EOFSA, we have a breakthrough instrument for a study of the sun. And EOFSA brings imaging spectroscopy for quantitative measurement of particles, magnetic fields, plasma in the flaring region. When we examine the results of this, our first opportunity to measure dynamic magnetic field behavior, we see exactly what we might have predicted: large-scale decay of the magnetic field, sufficient to provide the energy that goes into accelerating particles, heating the plasma, or plasma motions. The results suggest that although the reconnecting current sheet of the standard model gets things going, the main energy release that's powering the flare in this long-term acceleration is coming from a much larger volume. It's sort of happening simultaneously over this whole region, presumably due to enhanced diffusivity by turbulence. We don't really know exactly what the means of dissipation of the magnetic energy is, but again, turbulence is suspected. So future work would involve making similar measurements of many more flares and over a larger range of flare energies. And we'll also use EOFSA to investigate the transport and decay of high energy particles through the spatially resolved decay rates and conversion to thermal energy. So that concludes my talk. Guess I can take questions.
Thank you very much, Dale, for really interesting and concise talk. We are open for questions and comment. You can, in principle, just unmute your microphone and ask a question, given that we have a manageable group of people here. So I'm looking for microphones. Okay. Alexander Altentsov.
Good day. Great results, very impressive. And one question. I don't catch, do you have the sampleization measurements?
Yes. So EOFSA does make polarization. So we're measuring right-path circular polarization. Actually, we're measuring all four, essentially all four. So the calibration of that is still under study. So we're not that confident in our polarization results. So we're not really using that at this time. But in principle, we have all the calibration measurements that we need. We should be able to, once we finalize that calibration needs, we should be able to go back and include polarization in.
Yes, I see. Thank you.
Okay. More questions or comments? Meanwhile,
may I ask one more question?
Yeah.
Can you show the visibility plane? You have 13 antennas It's very interesting, the configuration and something like this.
I'm not sure I have anything ready for that. Unfortunately, I can send you something though. I'm working right now on a.
Thank you. It's interesting. Yes.
We can make a follow-up session with Dale and repeat these questions there and post online as additional short video.
I can say we're not that proud of our beam shape because it's with only 13 antennas. It's not a beautiful beam shape. Luckily, the calibration is pretty good. We're using large antennas with sensitive receivers, helium-cooled receivers to do the calibration, and that gives us excellent calibration, which allows us to do nice imaging even with the rather poor synthesized.
Yes, I understand that it is a great task. Yes, I see.
Yeah.
Okay. Do we have other questions? Sergey, go ahead.
So I have a question. So first of all, I would like to thank you for a great talk. And the question is rather technical. What techniques do you use to reconstruct images? Is it a usual clean algorithm or something different?
Yeah. So we first make images of just a snapshot of the flares, and then we use that to self-calibration. So we're using the flare source itself as a means to improve the calibration errors, and we actually do 2 rounds of calibration, self-calibration. One of them is using the kind of combining frequencies to improve the initial solution, and then we do a second round with individual. And once we've done that, then we apply just the ordinary clean tip to read.
Yeah, fun.
Hi, very nice talk, Dale. I'm just curious, in this region that you measure the magnetic field energy and the energetic particles.
Yeah.
Is this, correspond to the standard model? This is in the rooftop region?
So the choice of that region was mainly to avoid potentially bad fits. So this was a region of excellent fit in the entire box. If we go lower and a little bit closer to so you can see the region is actually sort of encompassing the newly closed loops. We anticipate that that's where the
so this is the tip of the closed loop.
Right.
Oh, okay.
Yeah.
So I'm just curious if that is the energy release region and their particles get accelerated, or?
Well, the point we're trying to make is that the energy release region is in the entire volume, full volume, showing similar behavior. So it's not concentrated in just that region, but the release of magnetic energy must be really distributed, which means that it's not coming from local reconnection in the current sheet, but has to be from some turbulent diffusion. Or suppositions.
Okay, look forward to the paper.
And this actually is a paper that Gregory Fleischman, the lead author on, and has been submitted, but we're waiting to hear.
Great.
Okay, more questions? I wonder, Dale, could you just give some numbers? How many flares were observed with EOFs and how many of them were like have been analyzed by now, at least partly?
So we have more than 100 flares of various sizes that have been observed with Gauss, mainly in 2017. So there haven't been any flares in 2018 to speak of. But they are of all sizes. We have maybe half a dozen that are large M or X class, and then another 20 or so that are reasonably M class flares, but many class and even B class. And I can show you, if I just skip over a couple of these. Here's another event that was studied by Natsuha Kuroda, and we see much the same thing happening. Like the white pixel here shows actually a relatively constant field, and then this red showing a decay at a lower rate. So this is about, I think it's an M1 there, and it has a lower rate of energy release, but it was really similar behavior.
Okay, thank you. Last chance to ask question or make comment. Everyone is muted, so thank you very much, all participants. Thank you very much, Dale. In 2 weeks from now, we won't have a webinar because it's Halloween. Might not be sufficient convenient for many people to attend, but in 4 weeks from now, we will be having next talk. Thank you very much. Yeah. Join next time.